In order to succeed with the green transition and reach our climate targets, hydrogen will have to be like an integral part of the future energy system, because there are several sectors today where we cannot use electricity directly, nor batteries, and where we need to replace fossil fuels with low-carbon hydrogen-based fuels. IFE, as a research institute, we are very hardware-oriented. The flexible and advanced nature of our labs gives us a unique position because we can bridge the research needs of academia on one side and industry on the other side. We both develop new concepts and we improve technologies, more efficient, more durable and more affordable. We work on different technologies along the whole value chain of hydrogen. So this includes both hydrogen production, storage and end-use technologies. So if we start with the hydrogen production technology, we follow two main routes. The first one is using water electrolysis to produce so-called green hydrogen using renewable electricity.
So in our lab, we specialize in low temperature fuel cells and water electrolysis. Our focus is on validation and qualification of different materials that goes into these units. Those materials include porous transport layers, catalyst-coated membrane, coatings for bipolar plates, new catalyst materials, new non-fluorinated membranes, because now we know there's a need to find alternatives. So we help support industry to develop these new solutions, and we help them to validate them using our state-of-the-art test stations.
The other route is to use gas. This can be both biogas and natural gas to produce so-called blue hydrogen in a process where CO2 capture is integrated.
We are standing in front of our SCR prototype, sorption enhanced reformer, which is producing hydrogen from natural gas or biogas. This technology combines both reforming, water gas shift and CO2 capture in one single reaction, and brings a certain process intensification to the whole process. This is made possible by the introduction of high temperature CO2 solvent, which is mixed together with a reforming catalyst to capture the CO2 while it is formed in the reformer reactor.
The challenge with hydrogen is that it's very voluminous and potentially dangerous if it's not handled properly. So therefore it's important to find safe and space-efficient means of storing hydrogen. At IFE, we work on 3 different hydrogen storage technologies. The first is geological underground storage.
We need to find very large volumes, and the best option, of course, will be in the subsurface, where we know that large quantities of oil and gas have been stored for millions of years. This is a typical reservoir rock, which can be used for hydrogen storage. It has a lot of small pores, but all together they create a large volume. Oh, look at this rock. Seemingly, you don't see anything, but this copper lenses in between, that can be hydrogen. We inject hydrogen into the rock, and then we look how hydrogen moves with respect to water. We want to understand how all this happens on the large scale. Hydrogen storage in the subsurface is just a natural choice.
The second one is solid-state storage in metal hydrides, and the third one is liquid hydrogen. We do advanced research and development of materials for hydrogen storage technologies. Very important to our focus on materials research is that we combine experimental techniques with computational methods such as DFT and machine learning. IFE has a long experience in producing and handling liquid hydrogen, and we are currently pioneering in a new method for hydrogen liquefaction using the so-called magnetocaloric effect. So in this case, we utilize a magnetic refrigeration cycle instead of the conventional refrigeration cycle taking use of like a compression and expansion of a gas. So this method is potentially game-changing because it can reduce the energy use related to cooling hydrogen down to 20 Kelvin with up to 50% compared to the conventional method. And then having produced and stored your hydrogen, you're going to want to use it as well. And at IFE, we do research on PEM fuel cell systems. So here we do both testing of the PEM fuel cell stacks, developing methods for condition monitoring. We're also testing key components of the balance of plant. And last but not least, we are developing and validated advanced method for energy management systems when you have a hybrid battery and fuel cell system. And this is very important when you have such hybrid configurations, that you have efficient and rational ways of sharing the load between the two components, depending on the drive cycle that you're using. I think it's very exciting to see when we are able to come up with an entirely new concept for hydrogen technologies.
And it's clear we all want a green energy. We all want a transition to renewable energy.
And we'll have a role to play for sure, because it's the only fuel which doesn't contain carbon.
We believe that hydrogen can be one of the solutions to this problem.
Of course, we would like to see the technology succeed and be a reality.
And when we see these technologies being deployed, that's always very exciting.